science is interdisciplinary? Do you also know that computer science is not just about a certain field, but rather it cuts across several fields? You want to talk of medicine, you want to talk of transport, you want to talk of education, economy, and so on and so forth. Today's video is going to be focused on computer science and understanding of how computer science is very, very important to the world. Let's take a preview of another conference. This was the one held in 2021 and focused on the Ampere architecture. All right, that's the predecessor to the Ada Lovelace, the one that was previously published on this channel. Okay, there we go.
One of the most exciting applications for AI is autonomous AI. This is essentially a data center on wheels, and AI is processing at real time.
Data center on wheels, one of the greatest. I like that introduction. We talk of computers. Computers are not just about web design and development and payment online. I get a lot of questions from people who ask that what has transport got to do with computer science? I believe seeing this presentation should give you a clear-cut answer to that inquest. Okay,
with sensor feeding it, and it has to process it so fast that it can make decisions in a split of a second. Autonomous vehicles is one of the greatest computing challenges, and will surely be one of the most impactful.
When we talk of computing challenges, we talk about real-time application of the theories learned in the class, in classrooms, where you learn about maybe theoretical Fortran and all those COBOL and the likes, and Visual Basic, VB.NET and all that. Most of all those programs, though, they are now fully object-oriented, and they're not just, if you learn them theoretically and you conceive them as real stepping stones to learning, your learning curve. Handling programming language in higher, perspective becomes very handy and quite easy to surmount.
It's one of the largest industries in the world. 10 trillion miles are driven each year. It is because of this we've created an architecture that is scalable. Ladies and gentlemen, today...
Now let me talk briefly about scalability. A lot of us might have been hearing about scalability. When you talk of scalability, think of it as an extension, something that extends. One of the biggest or one of the easiest examples I would love to give here is talk of the instance of a class. Usually we say an object is the instance of a class. So if you have a father class, a son of the father can extend the class of the father to inherit the properties and methods of the father class. Okay, so that's a very typical example of extension. Or you can talk of it in respect to being an annex. Annex, sort of an extension to the main house, the main building. So when we talk of scalability means that in computing context, scalability means something that can be improved upon, something that can be a stepping stone to a future, stones or milestones, as the case may be.
Announcing that the Ampere architecture is coming to Nvidia Drive.
Okay, now this is the Ampere architecture. Prior to this, there was the I think there were some microprocessors that was developed as a GPU. Okay, I might not be able to figure out the name here right now, but there were some previous microprocessing advances or architectures released by Nvidia. So this one is focused on Ampere. I think on an annual basis, these microprocessors are released in such a way that they become the basis of the graphical processing units produced by Nvidia. And of course, there are a lot of improvements to the output or the production of these cards compared to the previous ones.
Because of the scalability of the Ampere architecture, the efficiency, and the incredible computational performance, we can now scale our driving car computer from ADAS behind the windshield all the way up to robot taxis. From a low-powered chip for ADAS driver assistance to a powerful in-car computer for full self-driving autopilot, all the way up to driverless robot taxi. One single programmable architecture. This is basically the entire range.
Architectures improve. That's one thing we need to understand here. Architectures, and that's why, or I rather say that is one of the most intriguing things about computing science. Computer science is interdisciplinary. It cuts across various fields. You want to talk of education, you want to talk of finances, economy, engineering, medical science. Computer is not just, like I said earlier, it's not just static with web design and processing of payments and all that. There are a whole lot of extensions, or what I call it, applications of computer science, and this is one of it, as we are witnessing today.
Range of everything that moves, and it's our belief that everything that moves will eventually be autonomous.
If everything that moves will eventually become autonomous, according to Jensen, the CEO of Nvidia, that means we're going to be seeing a whole lot of devices being powered by softwares, applications, softwares driven by loops, iterations, and conditions or selections to form huge sequences of patterns and models and the likes.
Represent cars, passenger cars, taxis, trucks, shuttles, delivery bots. We're going to have autonomous vehicles of all kinds. The Ampere architecture will span this whole range. We also developed an end-to-end system for creating the AV autopilot application, testing it and simulating it, deploy it into the car, all the way to operating it with remote control. This entire system is built on one architecture. Nvidia is collecting data, labeling and augmenting the data, training the AI models. We created virtual reality driving simulation.
You should also take note that in artificial intelligence, machine learning, the higher or the bigger data you have, the more accurate the model becomes. It's very important you know this, especially for those of you that are very much interested in advancing your studies on artificial intelligence and big data. Now, what he's trying to say is that these vehicles, as they are tested in real time, they are going to be basis for gathering data, for training the data, for testing them, for validating them, and of course for eventually deploying them in real time with minimal errors, minimal or no errors. So we're looking at a very giant leap forward in this technology and this innovation in the nearest future.
Testing the entire stack in the car, to an AI agent that would assist you, all the way to a virtual reality telepresence system that allows you to portal into the mind of the car. So
now, those of you, you must have seen some of these things in movies and the likes, where someone will be in a place and will be connected remotely to some other device or some other fields or instrumentation, and will be controlling it. These things are variables. When you talk of virtual reality and the metaverse, these are just variables of the physical world that we all know, the ones we can perceive, we can see, and all that. So you think of them as variables and constants. You think, or probably you can say the physical world is the constant, and then the metaverse and the virtual world variables or objects are the variables that actually mimic the physical world, and that's what metaverse is all about. It's just about variables and constants. You build existing variables from constants and vice versa.
that you can remotely control the car. This end-to-end system and the entire scalable architecture from ADAS to autopilot to robot taxi is the Drive system. Now let me show you our latest update. Before I show it to you, let me first remind you everything you're about to see is in virtual reality. All of our engineers are safely sheltering at home. They could develop their application at home and virtually drive their autopilot in our data centers. Please enjoy.
Okay, so here, let me just pause a bit here and just give a brief enlightenment about this scene. Now, if you look very closely, you see that this particular, demonstration is showing some kind of bonding. We call them bonding boxes here. They are a type of software. They are bonding software algorithms that are written with 3D, and all that. Some of them are 3D, some of them are 2D. But this specific one is actually 3D, being used as a demonstration or in a live Tesla car or autonomous self-driving vehicle. Now, these bonding boxes are of different types. So many researchers worldwide have released different types. You have the MM segmentation, you have some of them are based on PyTorch, some of them are based on TensorFlow and the likes, and a whole lot of Keras and a lot of them. Now, what this does, the importance of this in an autonomous vehicle is that it makes image recognition and detection, very accurate, and it also implements high-level obstacle avoidance or collision avoidance, and this being computed into the mind or the operating system of the autonomous vehicles. It makes the vehicle much more, evasive of, incidents or issues while being tested in real time. And that's exactly what you're seeing. Because of this precision, the computer vision algorithm, it's called computer vision actually, it's an aspect of artificial intelligence, machine learning and likes, that makes a computer have sight for seeing, for perception, and for eventual absolute obstacle avoidance and collision avoidance as well. Now notice how this specific test drive, the autonomous vehicle maintains its lane, it maintains its boundary, it doesn't swerve out of it, and the like. And this is the product of very accurate models that have been built in the system and is actually makes it very, very intuitive and dependable. By the way, these vehicles are already being tested in China and parts of the United States, as well as some parts of Europe, like Germany, I guess, yes, and a few others. And the more these things are tested on the road, it becomes much more reliable. Like the places where it's being tested in the United States and China, I think they're already being tested alongside with manual driver, cars that are driven by humans. That's very, very lovely.
Wasn't that great? The Nvidia Drive platform is an open platform. We're doing so that we can...
Now, for the fact that it's mentioning that it's an open platform, indicates that it is genuinely a contribution to the progress of this innovation. Okay? And what that means is that for it to be open source, other software programmers or other people in this industry can key into it instead of reinventing the wheel or starting afresh, to develop something of this nature. Instead of starting afresh, of developing such innovations as this, this can be a milestone and then improved upon, such that this will become very, very easy to use, and of course right on the fly.
Understand the great challenges of this new computing form. Nvidia is developing the drive system from beginning to end, from the collection of data all the way to the testing of the cars. We're developing the entire stack from top to bottom, and we're creating an architecture that spans ADAS.
Now he's talking about stack, so it's very obvious, and it will be very accurate or precise to state here that for it to be a stack, you should know these autonomous vehicles will have at least an appreciable amount of software programming, software engineering processes embedded in the center, the core operating system, stacks. You should be looking at seeing a whole bunch of conditionals and selection, and of course iteration loops, and of course there will be lots of classes and methods and functions and so much more that will handle different components of the driving sequences, maybe the reversing, the moving forward, the side mirrors, the driver's mirror, the parking, the staying on the lane, the obstacle detection and avoidance, collision avoidance, and lots.
As to autopilot to robot taxis. This entire platform is open. You can engage the platform however you like. You could use our libraries, use our...
The engagement is very critical because of the open source community that will bring much more profit, much more, advances to these things.
Tools in any part of it to augment your own. The openness of our platform is the reason why we have so many partners around the world. Cars, trucks, Tier 1 OEMs, mobility services, startups, software companies, mapping companies, and simulation companies. We have partners all over the world using Drive, developing all kinds of different forms of autonomous transportation. This end-to-end pipeline, this end-to-end infrastructure is one of our greatest achievements. And we've learned so much in doing this about the future of autonomous vehicles.
Yeah, and that concludes it all.
Summary of what we have learned so far. Autonomous AI is one of the most crucial applications of artificial intelligence, indeed computer science. Additionally, it can be described as autonomous AI data center on wheels. Furthermore, This is practically depicted as AI processing on real time with sensors feeding and processing in split seconds. Nevertheless, it also faces one of the greatest computing challenges with the most. Here's the Nvidia Drive with Orin and Ampere as described by Jensen. Now you can see that the ADAS windshield end cap is the predecessor to the L2 Plus autopilot tops, and of course eventually this advances to applications in the robo-taxis. Okay, so another very important aspect that we should understand in this presentation is that these autonomous driving platforms have a sort of sequence of events. You have the sensing platform, you have the perception, the perception stage, then of course the mapping stage, then the planning stage, and then eventually the driving, which of course culminates in the fully autonomous self-driving vehicle platform. Now, it is also very important to state here that cars, passenger cars, taxis, trucks, shuttles, delivery buses will eventually be affected respectively, in the future with this sort of algorithm or this sort of innovation. Now, the background image you're seeing here depicts how integrated computer vision software sees and analyzes real-time images on the road with precision of obstacle collision avoidance, image recognition detection, and classification respectively. These all work together to have a very reliable and flawless autonomous vehicle system. And not forgetting that the bounding boxes you're seeing here is 2D. The 2D is still in operation, but in the future we're going to see more of the 3D, and then a correlation between the two-dimensional and the three-dimensional bounding boxes that aids the computer vision algorithm. Okay, so now I like the aspect of the period when Jensen was talking about data center on wheels. This is very true because autonomous vehicles, they have with the sensors they have and with other data trapping devices, the cameras, and so much more, it gives a sort of leverage to understanding real-time environments on the move. Okay, now this concept that I've drawn is just to actively summarize how autonomous vehicles are built, with respect to computational algorithms. You have the data collection, all right. There are already open source based research platforms, for researchers and programmers to build their understanding and advance their understanding and the application of autonomous or self-driving vehicles. You have the Lift Level 5 perception, you have the Kitty dataset, you have the new scenes, you have the LIDAR datasets, and the cityscapes. There are also so many, but I think these 5 or thereabout are about the major ones that are on the internet. Now, from here, you can now start training models through training, of course, testing and validating them from the data collected. Then from there, you can actually advance to the simulation, the actual driving simulation, where just like what the GCC 2020 presented that we've just seen, the simulation where the drivers are in their homes and then they are assisting in simulating or variating the real world through software and the likes. Now then eventually you now have the real-time autonomous driving, which of course is the physical world itself, okay, like what I also described during the presentation. Then the last aspect is the real-time deployment, okay, after it is tested and it is deployed in the autonomous vehicle. So the real-time deployment is when the users now take over and start using it. And of course research goes on because as these things are being used by humans, there's definitely going to be much more space for development. In conclusion, I want to make some very important facts known. You see, autonomous vehicles might be already perhaps in real-time testing in the United States, like parts of the United States, then of course China, maybe Germany, Japan, and maybe a few others. But in places like Africa, when I have these discussions with some academics and certain people, I tend to get this challenge that what does or how does autonomous driving or autonomous vehicles, re- become relevant to the context of the African environment? Uh, Let me tell you all something. The very first thing that you should know is that these advances are being done to save or salvage human lives in the future. Electric vehicles are going to reduce fossil fuel and the pollution of the environment. Already we are seeing the impact of climate change world over. There are snowstorms in the United States and in Europe. There is flooding in Africa, like Nigeria and a host of other places in the world, all because of the depletion of the ozone layer. So electric vehicles are going to could or stand as a middle tier that is going to cut probably the future of saving or completely destroying the world. Okay, every technology might have its own flaws, but there is much more advantage to autonomous vehicles than the disadvantages. Okay, we should know that. And I've also mentioned that the relevance of computer science is interdisciplinary. Okay, we should stop thinking that computer science or computer applications is just about web design, jQuery, JDs, JavaScript, and likes. It goes beyond these peripherals of just web operations. There's so many multifaceted applications to computer science. Part of my future work is going to involve deep learning and image processing with computer vision. Okay, now still in line with how relevant autonomous vehicles will be for our world, particularly Africa. I also get this challenge or this question from people that, take for instance Nigeria. They still a whole lot of, like, almost 99% of vehicles on the road are fossil driven, and they are still manually being driven. So they keep asking that, how does this thing relate to the Nigerian or the African context? All right, now during the presentation, you recall that the presenter of that conference, the keynote presenter, Jin Singh, the CEO of Nvidia, he mentioned or referred to something that has to do with scalability. Scalability is an extension. You extend to improve, and once you scale up, or once a resource is scalable, that means it can be extended. Modifications can be done to it. You don't need to necessarily reinvent the wheels. All right, Africa can tap into these innovations and these advances through transfer learning, and also be able to scale up and meet up with the rest of the world as these advances are taking place. Remember to give it a thumbs up, share, like, comment, and subscribe to our channel. Until next time, this is me signing out. Cheers and all the best.